Our next unit, Unit 2, talks about vectors. So let's start off simple and we'll build on everything that we cover. So what if I ask you to plot 2 points? P is at negative 2 comma 5 and Q is at negative 6, 3. Plot those 2 points and then connect them. Well, I happen to have done that for you. PQ is a vector that starts at P and ends at Q. Now, it's really important for you to understand that this notation here, don't confuse that with array in geometry. In geometry, that would mean array that starts at P and goes through Q forever and ever and ever. But when we're talking about vectors, it actually ends at Q. So it has a length. It's not an infinite length like array in geometry. All right, and so I have that vector graphed here. So it starts at P, and then it goes to Q, and that's where it stops. We refer to P as the initial point, and Q is the terminal point. So the initial point and the terminal point. Now we have different ways of representing a vector. So sometimes we'll use the 2 points, the 2 capital letters with the arrow above it, but sometimes you'll see it written as just a single lowercase letter with an arrow above it, or sometimes just a bold-faced lowercase letter. And so all 3 of those would be acceptable ways of referring to the vector. Now a vector has both magnitude and direction. So there's 2 quantities associated with a vector. Magnitude means the length of the vector, and the direction means which way is it headed. So for magnitude, the symbol that we use when we're talking about the magnitude almost looks like an absolute value. Now some texts will have a double bar on both sides of the vector, and some will only have a single bar. So when you see a single bar, don't get confused and think, wait, do they mean absolute value or do they mean magnitude? It depends on what is inside of there. So if that's a vector in there, then we know that these vertical bars mean magnitude. If it's a quantity, a number in there, then we know that these 2 vertical bars refer to absolute value. So you have to think about the context of the problem and decide what those symbols represent. So the vector that we just created, that PQ vector, go ahead and find the magnitude of that. And as always, might be a good idea to pause, come up with your answer, and then check. Okay, so we want the magnitude of this vector. Well, that would be the length. So I can think of 2 ways to do it. We could use the distance formula, difference of the x's squared plus the difference of the y squared, and then take the square root of that, which comes from the Pythagorean theorem, which is the change in x squared. So from negative 6 to negative 2, that was a distance of 4. And between 3 and 5, that was a length of 2. So we could use Pythagorean theorem, and we're going to get for this the square root of 20, which we can simplify as 2 root 5. And you should always simplify your square roots. So the magnitude is going to be the square root of 20, which equals 2 root 5. Now if you had used the distance formula, you would have gotten the same answer. So the difference of the x's, what did we have? We had a negative 6 and a negative 2, right? So negative 6 minus negative 2 squared plus, and then the difference of the y's, 3 minus 5 squared. And then we take the square root of that. And so then that's going to give us the square root of negative 4 squared, which is 16, and negative 2 squared is 4, and there's your square root of 20. So whatever way you want to do it is fine. What's the slope of this vector? So let's go back and look at it. Well, the easiest way is to count what's the rise over the run. So and we want to start at P and go to Q. So we went down 2, that would be a negative 2. And then we went 4 to the left, that would be negative 4. So that's a positive 1/2 slope. If you started at Q and went to P, it's still the same. It's up 2 and 4 to the right. So that's still positive 2, positive 4 equals 1/2. So in either case, we get a slope of 1/2. Later, we'll refer to the slope of this in terms of the angle it makes with the horizontal. But for now, that's good enough. Okay. Now, what if we have two vectors? How do we know if they're equal? Well, they're going to be equal if they have the same magnitude and direction. So they can't just be the same length. They're not going to be equal if they're not going in the same direction. And likewise, two vectors that are parallel aren't equal unless they have the same length. So both of these conditions have to be met. So let's take two more points, M at the origin and N at -4, -2. Is the vector Mn going to be equal to the vector PQ? So let's go back to the picture here. And let me move this out of the way. And I believe, there we go, there's vector Mn. Let's get rid of all this other stuff too. We'll just throw it around. Yeah. All right, are those two vectors equal? Well, first of all, do they have the same magnitude? Well, yeah, you can tell if we use the Pythagorean theorem again, or the distance formula, that we're going to get the square root of 20 for the magnitude of vector Mn. And then in terms of slope, it also has a slope of 1/2. So the answer to that question is yes. Sometimes, instead of having vectors all over the plane, it's easier to refer to a vector in what we call component form. And then that's an easier way to match and decide if vectors are equal. So the component form of both of these vectors is -4, -2. And sometimes you'll see it written, and I believe in your textbook, they're going to write it this way. Almost like we would write a 2x1 matrix. So either notation is fine, but that's the component form of a vector. And where does that come from? Well, you take your initial point, and as you're traveling to the terminal point, first in the x direction, how far do you have to go? And that's 4 units to the left, so that's -4. And then how many units in the y direction? Down 2, so that's -2. So the component form is -4, -2. And that would be, excuse me, the same as the component form for Mn. That also goes 4 to the left and 2 down. So when we use that component form notation, we can refer to many, many different vectors. We refer to that -4 as the horizontal component and the -2 as the vertical component. So let's look at another example. Write the component form of the vector W with an initial point at 7, -1 and a terminal point at 4, 5. Well, I guess we could plot these and then we could just count from 7, -1 to 4, 5. How many in the x direction? Looks like we're going back 3 or left 3. And then how many in the y direction? Looks like we're going up 6. And so sure enough, that's the component form of this vector. And once again, if you want to write it vertically like that, that would be fine. So to get the component form of a vector, you simply subtract the x coordinates and subtract the y coordinates, but the order is important, and you want to make sure that you're doing terminal minus initial. So the terminal point minus the initial point, and that'll give you the component form. And now what if we want to find the magnitude of this new vector from this example? The vector W which has a component form of -3, 6. Well, just like we did before, when we used the distance formula, when it's in component form, it's even easier because then we can just do the square root of the x component squared plus the y component squared. And so that's going to give us the square root of 9 plus 36, which is 45, which is 3 times the square root of 5. All right. Let's try to look at some other vectors. Let's draw the vector u, and the component form is 3, 4. And then I'd like to draw twice that vector, or 2u. And then I'd also like to draw negative u, or the opposite of u. So let me show you what that looks like. So here's vector u. To do twice u, well, we're just going to make it twice as long going in the same direction. So that would be 2u. And then negative u, well, that's just going to go in the opposite direction but keep the same length. And so geometrically, that's what it's looking like. Let's write the component form of 2u. Well, you can look back at it, but the component form, it went 3 and 4, and then it went another 3 and another 4, so it's going to wind up being 6, 8. And yes, you guessed it, to do a scalar times a vector, you just multiply that scalar times each component, the x component and the y component, and you get that. What about the component form of negative u? Well, you can think of it as negative 1 times the vector 3, 4. And so that's going to give you negative 3, negative 4. All right. Let's take another vector v, and let's have that vector be negative 2, 1. So picture that. I've got it right there. There's v in green. Negative 2, 1. And then let's take vector u from before. So I drew the same vector u from before, which was 3, 4. And let's draw u plus v. What does it mean to add two vectors? So first let's get a geometric representation of this. To add two vectors, if I want to add u plus v, basically that means you're going to start at u's initial point and travel to its terminal point. And then from there, we're going to go in the direction that v tells us. So we're really doing, they call it tip to tail. So we take the tip of the first vector and then the tail of the second vector starts right there. And so after adding those together, the resultant vector is that, u plus v. So when you want to add two vectors, you take the first vector, then you slide that second vector over so its initial point is at the terminal point of the first vector. The green initial point is at the terminal point of blue. And then your resultant vector is where you originally started to where you ended up at the end. And that's the red vector. Now, if I make a copy of this, slide it over here, and if I make a copy of this one, you'll notice that the green and blue vector, if I make extra copies, they really determine a parallelogram. And so u plus v winds up being one of the diagonals of that parallelogram. And that's referred to as the parallelogram law. And if I do v plus u, go back to my picture, that means I start with v, the green vector, and then I add u, the blue vector. I still get that same resultant vector. So that tells us that addition of vectors is commutative. I'll say that one more time. Addition of vectors is commutative. Now, if we're not looking at a picture, adding two vectors simply means you add the x components and you add the y components. And multiplying a vector times a scalar, or a constant, we multiply each component by that constant. So the arithmetic involved with vectors is really easy. And it's exactly what it seems like it should be. Now, what about if I did, instead of u plus v, what's u minus v? And that gets a little more complicated. So here's what I'm going to do. Let's take this vector v, and to make u minus v, I want to think of it as u plus the opposite of v. So the opposite of v is going to be that vector. Maybe I should change the color. Let's make it, oh, I don't know, purple. So that's negative v. And so when I do u plus negative v, I'm going to wind up with that resultant vector, which goes from here to here. So that's going to be u minus v. But notice, if I go back and make my parallelogram, that winds up being the other diagonal, or it's equal to the other diagonal of that parallelogram. So adding two vectors gives you one diagonal of the parallelogram that they determine, and subtracting gives the opposite, or the other diagonal for that. All right. There's a second set of notes on vectors, but you can at least do some of the problems from worksheet 1.2. But for some of the questions, you're going to need to watch the next video.